Hi, everybody. Now I was talking to my kids last. Anyway, never not first, evaluating a limit. Got to start over. Plug in a zero, you get 0/0. Okay, now it's okay. It's okay. Let's focus on the math. The problem is that there's an X in the top causing a zero and an X in the bottom causing a zero, but also the sign. I can't factor out the problem area. So none of the methods that we learned in 1.4 will work here. None of them. None of the algebraic reconciliations will actually reconcile it. So what else do we have? And quit looking at what's everyone looking at my forehead? My eyes are here. What do we have in our mathematical tool bag that we can use here? L'Hopital's rule. We can lop it. Thank you, Johann Bernoulli, right? So because we showed 0/0, we can say lop it. And I like to put the nurse's hat on it still. Lop it, colon, right? That is like that's like label, that's stage notes for the person grading your work. Okay. Let's lop it. We need the limit still, don't we? You don't want to be careless and lose points. Because on a free response, it's been showing up the last few years as one part on a free response. On a multiple choice, I'm sure there's a few that appear, they don't release those. You don't have to write lop it. You can save time. But you got to practice the notation so that you know how to use it, right? It's not Hody high, remember. It's just straight up derivative of the top over the derivative of the bottom. And then you simplify again, but there's really nothing to simplify. So we'll try direct substitution once again, and we get 0/0. Cosine of 0 is 1. Can we lop it again? Yeah. Now, don't say this. Don't say prune it, right? Because that won't quite work, prune it, right? But that's what you use loppers for pruning. Yes. You got to write lop it again. Every time you use L'Hopital's rule, you got to write indicate it, because otherwise people think that you're using witchcraft. They'll assume the worst if you don't indicate your method. It's when you do things algebraically, that naturally follows from a sequence. You don't have to label what you're doing when you're doing algebraic manipulation. But when you're pulling out a theorem or a special trick, if you will, you got to tell people what you're doing. The limit as x goes to 0, 6x over negative sine of x, remember, minus 0. We still can't divide out the problem area, but we can use direct sub. In the top, we get 0. Bottom, we get 0. Oh my gosh. There's not going to be much of this tree left after we're done lopping it. Right? By the way, you should lop your crepe myrtles every Valentine's Day. It's an easy way to remember. Crepe myrtle is a flowering shrub, bush tree. Yeah, the purple and yeah.
She put one in. It's grown like a witch. It's huge.
Yeah, they're nice. But if you lop them every February 14th, they'll grow back bigger, stronger, better. Yeah. All right, one more time. The derivative of 6x is 6. The derivative of negative sine is negative cosine. And now we know we're making progress, because if you notice what's happening every time we take the derivative to the degree of the numerator.
It's just the variable's gone now.
Yeah, it's a polynomial, so it's decreasing and the variable will eventually disappear and it's gone. So now we know we're going to get a final answer. You get 6 over, negative 1. Or cosine of 0. If this is a free response, could you actually stop there? You could. You actually could. Okay, but you could also continue. Cosine of 0 is negative 1, and so you do get negative 6. Negative 6 would be the multiple choice answer. So yes, you can do repetitive L'Hopital's rules as long as you're indicating 0/0 and saying what you're doing. And so this one we used it 3 times. This is in the ballpark of what you could see on the AP exam. Okay, there's not a lot of triples out there, but there are several doubles. We use it twice. Okay, moving on then. We are on, I think everyone has a firm grasp on the information the derivative can get us. And the number line chart that we create, although it gets no official credit, no awards, no ribbons pinned on it, it helps you win at other things, right? It helps you win, right? You can't just buy the weight bench. You have to lift the weights.
Amen.
Amen. Right. And I will just say, as a strategy, weights are easier to lift when they're lighter. So
You can't just buy the Pro V1s. You gotta hit them.
example 5. You know what? Let's do this. I do actually want to come back and work this one. So here, I'm sorry, my brain is all over the place trying to amend and cut and make things better and smoother. But as I was talking with someone yesterday, it's just it's so hard to get rid of things that you've labored over and judiciously chose in the beginning because it indicated something was good about it. There was a learning point or technique that we had to extract from that problem. So I don't want to skip it. So I know you can't amend yours because I already wrote something underneath it. So just add a new page, copy that image, and we'll go from there. We're learning all kinds of things. We're kind of right now building the plane as we're flying it, but it's okay. We're building the inside of the plane. Okay, the plane outside, mechanics, it's worthy of flight. All right, so we're trying to find the relative extrema. If it says to find the relative extrema, that technically means the y values, right? Because the max and min are the y values. So to do that, we need to first find the x values where the relative extrema occur. And they can only occur for continuous functions at what types of values? Critical values. Good. And critical values are values where the first derivative is 0 or undefined. 0 or undefined. So you always want to size up the function first. What is its domain? Anyone? What values of x work here? Yes, very good, very good. Bear in mind that this is the same as this. I'm sorry, as this. But since you noticed it, this was one of the other things that this is actually how I started the conversation with my kids yesterday. Because it was National Bird Day. And I told them Happy National Bird Day. And so we got to talk about those. And so I went off in dad mode and I was just walking around the house going, cuss flirt, cuss flirt. My wife is, what is wrong with you? Right? These next 25 years aren't going to be very easy. And so I said, no, Mike, Tate and Jenna know what I'm talking about. Tell them, Tate, tell them, Jenna. Shut up, Dad. Shut up, Dad. Shut up, Dad. But yeah, y'all know what it means. No, they don't. No, they back up their mom, but that's okay. I can fight 3 at once. The dogs like me. My 2 dogs like me if I have food. We are on cuss flirt because I have an exponent that is in what interval? Between 0 and 1. Okay. So when other people don't even find them at the end, you're finding them at the very beginning. Okay. There are going to be 2 critical values where the function's defined, but the derivative is not. They're going to be vertical tangents. And they could be vertical tangents that go straight up and continue to increase or decrease through them. That would be increase to y'all, decrease to y'all. But it could also be a local min or namaste, a local max. Okay. What are the 2 roots? What are the 2 roots of this base? What 2 values make this 0? X plus or minus 2. So we know right away at 2 and -2, we're going to have critical values. The domain is actually all real numbers, right? We're taking the cube root, so negatives under the radical are still permitted, but oh, by the way, we're squaring the quantity, so we're not even going to have negative values. This graph lives entirely either on or above the x-axis. Let's find the critical values. If you want to say the domain is all real numbers, the domain of f, that's important because remember, if the domain's not all real numbers, if there is a discontinuity, if there is a vertical asymptote, the function's not defined there, so neither will the derivative. And that guy might show up as a critical value. So f prime equals chain rule, right? 2/3 blob to the -1/3. We're done with the derivative, but now we got to clean it up. Because we're using it now, we got to clean it up. Times 2x. Good, good. I just felt like unsettling. in the whole room. It's good. That was good energy. That was like but energy, right? Let's clean it up now. So this is really 2x over 1. This is all over 1. So we have factors of 2 and 2x in the top. So that's going to be a 4x. And in the bottom, we have factors of 3 and that other big thing, right? Which I'm going to go ahead and say it's back under a cube root. You could put it to the 1/3 in the denominator, but here's what I would recommend. Because we are fixing to use it, I think we think better in terms of radicals. If we're trying to evaluate something, if I say what's 8 to the 1/3, you might say 8/3. But if I say what's the cube root of 8, you'd be like 8/3. Nah, it's 2, right? So when we're using it, maybe put it back in radical format. Now, there's really nothing to do except maybe factor under the radical x minus 2x plus 2. I don't know if that's quite worth it or not, because you can look at it and know that the two roots you already said were 2 and -2. So this would be your full-fledged factored version of the derivative, or your yeah, that prime. So now we want to know where it's equal to 0 or undefined. Think about the undefined always first. The function originally f did not have a denominator with variables in it. All of a sudden the derivative does. Okay, and we kind of anticipated that. So what we're going to do now is we're going to use it twice. We're going to say f prime equals dne, and that's going to happen when the denominator is 0. So we're going to set the denominator equal to 0. And of course, now how would you solve that? You would peel back the layers. You would divide by 3. 0 divided by 3 is 0. You'd cube both sides. 0 cubed is 0. You'd factor it or separate. You could just go straight to x equals plus or minus 2. Those are the ones we knew in the beginning because we were on cusplert. All right, if you don't know what cusplert means, what does never done first mean? I said, shut up, Dad. Did you not hear? Go grab some Q-tips. I made that. They're not that mean. We play with each other a lot. It's all fun and games. What? Oh, yeah, because I didn't hear. We told you to shut up the first time. You're still going. It's not that I didn't hear him. It's just that you can't stop, won't stop. Can't stop, won't stop. Try to let the dad jokes drop. And now we'll say f prime equals 0. When is a fraction equal to 0? Not when the denominator is 0, but when the numerator is equal to 0. We have to show that. We always have to show the equation we're solving. And so there we go. How many critical values do we have total? 3. Do we have any discontinuities? Any discontinuities of f? I'm sorry. No. Because remember, a sign of f prime can also change at a discontinuity of f. But we don't have any of those. So if we did, we would put them in the number line chart. But right now, it's continuous for all real numbers. We only have 3 critical values. 3 critical value means we have 4 intervals to test. Always one more interval than critical value. So it's time for the number line chart. We got x. We got f prime. There's the number line. -2, 0, 2. Turn it into a chart with rows and columns. Put your critical values up here. Circle them. Make them bigger. Make them stand out, because those are the ones that we're interested in. But for now, we're going to find some sacrificial values. Any number to the left of 2, how about -3? Any number to the left of 0, but greater than -1, 1, and 3, right? Make it easy on yourself unless you're really, really into a challenge. Okay. And now we're going to plug those values back into the and see what the sign is. SIGN sign. Okay. So here we go. When I plug in a -3, I get a negative in the top. And if you don't want to remember that, just write down a negative divided by, what do we get in the bottom? Positive, right? -3 squared is 9. 9 minus 4 is a positive. The cube root of a positive is positive. Positive times 3 is positive. What's a negative divided by a positive? Negative. So we get a negative in that interval. Okay. All right. It's fun. It's easy. It's fun easy. Plug in a -1, you get a negative in the top. What do you get in the bottom? -1 squared is 1. 1 minus 4 is -3. -3 is not a perfect cube, but we don't care. The cube root of a negative number is also a negative number. And that negative number times 3 makes the denominator negative. What's a negative divided by a negative? Positive. Yep. Plug in a 1. In the top, we get a positive. In the bottom, we get a negative. Positive divided by negative is negative. And then we plug in a 3. We get positive, positive. My kind of guy. So that's positive. Right? So we have our signs, and it's like, okay, guys, now you may exit stage left, or you can throw them into the spike pit, whatever. Oh, that sounds drastic.
Spike pit.
Yeah, spike pit, a pit with spikes in it.
Yes, sir.
Yeah, thank you for your service. You sacrificed well. Okay. No, how about exit stage left, pick up your broken toaster and head home? How about that? Yeah. Just for participating, you get a broken toaster. We can answer the questions now. Where's the function increasing, decreasing, and what are the local extrema? Let's go ahead and do both. Okay, we'll change the instructions. F is increasing on any interval where you have a plus sign. So it's going to be between -2 and 0, union to the right of 2. Okay, and we're doing open intervals. Okay. College Board may have brackets around those. Don't let that bother you, okay? Don't let that bother you. And decreasing, we're still using the subject F. No, but we can talk about it. We don't have to write it. Oh, it says, okay, let's do so then. Yeah. From negative infinity to -2, union 0 to 2. See, that's why I married well, because, you know, those are my family has good ideas, right? Like you just had a good idea. I'm always trying to just, no. They're like, no, you need to wear the helmet, Dad. Okay. So let's go ahead and justify. With notability, we can move this down, okay? F is increasing on those intervals because F prime is what on those intervals? Greater than 0. Yeah, on these intervals. And then it's decreasing on that interval because F prime is less than 0 on these intervals. Okay. And again, judicious use of the pronoun, collective pronoun these. We know what the antecedent is. Just be very careful. When it's an interval like that, that's a lot of writing. But if it's just like at x equals 5, it's easier just to write at x equals 5 than write at this point. Okay. So when you're justifying, what's that? Right. We're using F here, not F prime, because F prime's sign tells us what F is doing. Okay. So because F prime is positive, its function F is increasing. Okay. If you accidentally said F prime is increasing here, you're actually talking about the change in F prime, which is really the second derivative. And we're getting to that next section. That's concavity. Okay. So yeah, you got to be careful what you're using. Now I put a lot of asterisks here because what I'm about to write and say is very important. Just for the rest of the year, when you're justifying, always, never not always, discuss or use whatever signs, that means positive or negative, not like there was a comet last night. That could be a sign of impending doom. Have y'all seen the movie Don't Look Up? I saw it. It was great. Always discuss the signs, positive or negative, or the change in signs. Okay, from positive to negative or negative to positive. All the time, every time, never, not always. Okay. So don't ever justify anything by saying it is increasing on this interval. Rather say its derivative, whatever that is increasing on, is positive on this interval. Does that make sense? That'll get you through everything. Very important. And of course, I'll keep reiterating that. It's funny, iterate means to say again. So reiterate is really to say again and again, like when my family tells me to shut up, Dad. All right. Now let's go back to the first derivative test. The two values that came from the derivative being undefined are going to be critical values that look like one of these four. It's going to be a vertical tangent that's increasing, vertical tangent that's decreasing, a vertical tangent that's a local max, or vertical tangent that's a local min. It's going to be one of these four. And of course, the critical value we got at 0 from where the derivative was 0, or the horizontal tangent line, it's going to be like this. It's going to increase through the horizontal asymptote, decrease through the horizontal asymptote. See lunch today. I love it. Local min or local max. Okay. I didn't put dots on these over here. I guess I could do it here, but I didn't want to blunt the cusp. Okay. But those are the critical values, right? So how are we going to know which it is? There's a number line chart, right? So when something goes from negative to positive derivative wise, the function goes from decreasing to increasing. So which of these four is that one? It's that one. So instead of drawing it like this, like we did yesterday, which is if it had a horizontal tangent line, you can actually do it like this. And that gives yourself a little bit more information. Now 0, remember, was the horizontal tangent line. So if a derivative goes from positive to negative, the function goes from increasing to decreasing. And so it has to look like that. And so we'll do this, increasing, decreasing. And then of course, the other one is decreasing, increasing. So 2 birds in a hill, right? 2 birds in a hill. Now we can answer the question, all right, about local max and min. Here's the cool thing. There's 2 local mins. You don't have to justify them individually. You can clump them together, okay? Now, here's a really important thing. Local extrema can only occur at critical values. Do we have to restate that x equals -2 and 2 and 0 are critical values? Or is our work that we've already done finding them sufficient? It's that one, okay? It's that one. So if you're finding your own critical values and you're declaring them, they can look at the chart to see that you're using them and they see that you found them. You don't have to declare these are the critical values. We know that they are. But there'll be later where we're not told what the critical values are. We didn't find them. We don't have the equation and they're just saying determine if something has a local max or min at this point. We would have to first state that it is a critical value, but we don't have to do that here. So let's just jump into the 2 local mins. F has local mins. Now we got to be careful here. Are we just looking for the x values or do we want the x and the y values? Find the exact values of any relative extrema. Those are the y values. Okay, so no big deal. No big deal. We'll just say F has local mins. Let's do these one at a time, but in the same sentence. We'll say at or of. Let's do of. Of means you're doing the y value. So let's do the first one. How do I find the y value at -2?
I have a question.
Yeah,
What if it says find a relative extreme?
that's the same as local extrema. That means we need to find the y values. Yeah. If it only wants you to find the x values, it'll say there is something on my forehead. It'll say find the x values. Okay. If it says local extrema, that's really the y values, but we'll talk about the x values too. So F has a local minimum of y equals, and we'll just plug it in. Well, I think we already kind of know what the answer is. What do you get when you plug a -2 in to F? 0, right? You get 0. F has a local min of y equals 0 at x equals -2. Okay, so this is the location. When it says at, that's the x equals. And at y equals y, I'm sorry, and of y equals 0 at x equals 2. So I'm listing not just the 2 x values, but the corresponding y values, and they're the same. You don't really want to list it as an ordered pair because the maximum value itself is the y value. The x is just the location. And now we can justify. We can say because f prime changes from negative to positive at x equals plus or minus 2. Done. Boom. So it's not always that you're going to be asked to find the y values as well. Most of the time, they know that if you find an x value and they give you the function, any algebra 2, algebra 1 student can just plug and chug and find it, right? So they're really concerned with your argument and the x values, but you do have to read carefully. Of is the y value, at is the x value, the location. Now, again, we don't have to state that f prime is d and e there because we've already found that, okay? And f has a, I'll use the other term this time, relative max of, and what is it? Let's see, y equals, that's at 0. So if I come up here and plug a 0, that's where this one is handier, right? Because you don't want to think negative 4 to the 2/3. Although on a free response, you can leave it as negative 4 to the 2/3. But if it's a multiple choice, let's see, plug in a 0. What's negative 4 squared? Positive 16. And then we get the cube root of 16. Is that a perfect cube? No. It's the cube root of 16 at x equals 0. Okay. And then it would be because, and then here's the typical thing, right? F prime changes from positive to negative. Where? In France? No, at x equals 0. I read yesterday that there's like a new variant that was just found in France. And it's a weird name. It's not like just a Greek letter just yet. So it's a fluvid. But you got to say it with the French accent, right? Try that, Mason. Say fluvid with the French accent. I don't even know what a French is. Baguette. There you go. All right, now let's do one last thing here. We answered the question. Really, the whole point of doing this type of stuff is to gather information about what the graph looks like so that we can see behavior, right? You can predict analytically, but when you see a graph, you easily see at a glance what the overall behavior is. So let's go ahead and put together all the stuff that we've learned in our lifetime, including the ABCs, to try and sketch this graph. Well, we already said that because the whole thing is going to be squared and then the cube root of a squared number is either 0 at the smallest or bigger, I know it's going to live above the y-axis, okay? What about the domain? The domain's all real numbers, right? So we actually have points that we can plot. We have the point 0 or 2, 0 and negative 2, 0. Let's plot those. Negative 2, 0, positive 2, 0. Move that over a little bit. Try to make it the same, right? And then we have this other point 0, comma, cube root of 16. Now, there's one other thing that we can use here that would be to our benefit. Symmetry. It seems like the data has been coming to us symmetrically, right? Negative 2, 0, positive 2. There you go. This function is an even function. What is an even function algebraically? When you replace x with negative x or a positive number with a negative number, do you get the same output? And the answer is yeah, because there's only one variable and it's squared. So it has y-axis symmetry. And so now with our number line chart, we know that it has to kind of look like that. And it is continuous. So yeah, it's going to come like this. It's going to go vertical. Actually, let's do this. It's going to come in like this. And it's going to go vertical. And then it's going to come out of vertical and go horizontal. And then symmetrically, it's going to go vertical and go back out like that. Okay. So it kind of looks like a W, right? I did it in orange because it's almost lunchtime and we live in Texas. Whataburger. There you go. Whataburger. It looks like the Whataburger logo. Yeah. So that's what it looks like. And now at a glance, we kind of get to see what's happening, right? There you go. Now, believe it or not, we can determine the curvature of this graph just from what we've already done. Curvature is concavity. Concavity is not concave convex, it's concave up, concave down. That's what we say in math, right? There's no convex. Concave up is like a cup, concave down is like a frown. This is part of a frown, so it's concave down. This is an entire frown, so it's concave down. And this is part of a frown, so it's concave down. So this graph is frowning everywhere. It's concave down, okay? Oh, no, I don't know. It turns out that the second derivative gives us the curvature. So if we know this graph is concave down everywhere except -2 and 2. Why is the curvature undefined at -2 and 2? Because if the second derivative gives us curvature and the first derivative is undefined there, the second derivative will have to be undefined there. Yeah, once you hit an undefined point, the subsequent derivatives don't exist. So there's no curvature there. It's actually pointing. But for everywhere except -2 and 2, the second derivative is negative, okay? So sometimes we'll be using the second derivative to help us determine the curvature. If we know what the concavity or curvature is, we can use it to answer the second derivative. DQ, that's what I like about Texas. All right. Let's come back up here. Or down here. Yeah. Now example 5 with the calculator. And here it is. In my best penmanship, it was always my worst subject, penmanship. If I write in cursive, it's a little better, but my print is horrible, okay? But it's legible, I think, right? Calculator permitted. Find the x coordinates. There it is. Find the x coordinates only of any relative extrema of the function g, okay? And you're like, g, what is g? Because this doesn't apply. This is gone. If g prime is x cubed sine of x on the interval from -4 to 4. Okay. How do I see? Let's see. Okay. So I don't know the function g, but I do know its derivative. If you want to come grab a calculator, you can. Come on. While I'm talking, you can grab a calculator. I'm going to use the online one. Well, let's think about it. I don't know what the function g is, but if I'm trying to find its relative or local extrema, first of all, I know they can only occur at critical values, which is where its derivative, which we have, is 0 or undefined. And then if I analyze the sign of the first derivative on either side, I can determine if it's in. So I don't really need g if they gave me the derivative, right? I can still talk about g without knowing what g is if I know g prime. So this is a calculator question. Let us go to the calculator. I'll pull this one up here. Okay. Boom. There it is. All right. Now I'm going to just turn these off because I need that equation next period. We're doing logistics. So I'm going to use Y2, but y'all can use Y1 or whatever. You can turn again a graph off, but just by clicking enter on the equal sign, it unhighlights it. So I'm typing in this derivative here. We can't solve this one without a calculator, really. I think we can. Well, we probably can. We actually can. But I want, yeah, okay. Let's pretend we can. Let's type this in, x cubed, and then sine of x. Now, anytime we hit sine of x, or cosine of x, or tangent of x, we need to make sure we're in radian mode. So if you want to hit mode, double check. Okay. Now, this function, the derivative function, we're only looking on the closed interval from -4 to 4. So I'm going to go straight to my window now before I graph it. And I'm going to change my x min to -4 and my x max to 4. If you want to leave your scale at 1, you can. I always turn mine off because I don't really need to see those tick marks. They actually kind of tick me off a little bit, especially when there's too many of them. They give me fat axis, and I don't want fat axis, right? New Year's resolution, less fat axis. All right, turn your X scale, Y scale off. Now, we're looking for where the derivative is undefined, but will the derivative be undefined? Will the derivative be d and e if it's x cubed times sine of x? No, because those are two continuous functions, and the product of two continuous functions is yet another continuous function. So we know we're only looking for zeros. When you're trying to find an x-intercept, You want to keep your x-axis in the middle. And by default, it is. Your y's go from -10 to 10. We coughed at the same time. I'm going to go always, though, from like -3 to 3. And what that does is just stretches out your scale, because sometimes College Board, they'll craft a question where it's hugging the x-axis and you don't know if it's touching or crossing, and you have to zoom in, and it's a pain. So if you just stretch it out to begin with, you're only looking for where it darts across, and then your y scale can be at 0. And again, we set it from -4 to 4 because we don't want to be tempted by outside values. Okay. Now, looking at this, this is the derivative. How many critical values does it appear we have? It looks like it has 3, right? One over here on the left, one over there on the right, and it looks like it's symmetric. And then it appears that there's one at 0, right? Now, here's what I was talking about. You didn't do from -4 to 4. Don't be tempted by outside critical values. Oh, you did?
I just didn't change the y.
Oh, that's okay. Oh, that's right. I was like this. I should have done like this. Okay, that's fine. Y'all's are blue. I'm just jealous. -4 to 4. So yeah, so I stretched it out vertically, but look at the origin. That's what I'm talking about. Does it touch, or does it actually cross there? How can we determine? You could zoom in, or in this case, you could hit trace, type in a 0, and it looks like it gives you 0, right? But when in doubt, you could zoom in. But I think it just bounces one time. Okay. Now watch this. Without even finding any of the other 2 x values, how many local extrema does the function have? That local extrema, remember, means max or mins.
3?
No. 2. It has 2 local extrema. That's the type of question that can show up independently on a multiple choice question. They'll give you G prime and they'll say, how many local extrema, max or mins, does the function have if G prime is this? There's a critical value. We don't need a number line chart. You know why? We have something better than the number line chart. We not only know the sign of the derivative on either side, we have a view of the relative y values, their value. So watch this. If this is where it crosses, that's a critical value. Immediately to the left, the derivative is negative, and immediately to the right, the derivative is positive. You're having to train your brain to look at this differently. When a derivative goes from negative to positive, the function goes from decreasing to increasing. So that's the location of a local min, right? Here's a critical value, but on either side, the derivative is positive. So it's increasing through there. It's some type of horizontal tangent, kind of like x cubed. And then over here, there is a sign change. So we know it's going to be a local extrema, but the derivative goes from positive to negative. So the function goes from increasing to decreasing. Okay. So there's one local max, one local min, and the other one's just a critical value stationary point. Okay. So you can get that really, really quickly. Even with a much more elaborate graph, you're just counting how many times the graph crosses the x-axis. Okay. Pretty cool. So we're just trying to find the x coordinate. So we'll just say G, not G prime, right, has a local, what do we say, min at x equals, crap, we didn't find it, did we? We just talked about it. How do we find it? Well, there's 2 ways. You could go second trace number 2, all right? It does have a way to find a 0, but you have to scroll to the left of where it crosses, then scroll to the right of where it crosses. What I would always recommend is just to go to Y2, or I have to go to Y3, and just graph 0. Graph the y-axis, or the x-axis, sorry. Just graph the x-axis and hit graph again. You're not going to see it. I'm not going to see it. You're going to see it because your axis is going to turn red, which means it's probably going to eat a booger soon, right? Cougars, right? But now watch, second trace, since I technically have 2 graphs, I could use 5, which is faster. Watch, why is it faster? Here's your first curve. Is that the one you want? Yeah, look at the top. That's one of them. Hit enter. It's going to automatically throw you on the other curve. Is that the second one? Yeah, hit enter. And now for the guess, all we have to do is scroll towards the closer one. That's it. Okay, until you're close to it. Yeah, and then hit enter. So hitting enter is a lot faster, I think, than scroll to the left, scroll to the right.
Very right.
Okay, I'll take it. I'll take it. I'll take it. I'll take it. All right, now it's 3.14159. 3.0. I just graphed 0, the x-axis. X equals 3.14159. That looks a lot like what? Pi. That is pi. Okay. You could say pi, or you can go to 3 decimals here. If it is a calculator question, 3.141. And then it would be because, I'll just put BC like that, because G prime changes from negative to positive at X equals 3.141. Okay.
Would this one be, should it be negative? Because you were trying to find the left one, but it went to the right one.
Oh, yeah, that's what I was trying. Yeah, I'm still thinking of it. I don't know why it jumped all the way across and gave me that one. But yeah, if I'm justifying that one, it should be the negative. Yeah. My bad. Yeah. And so now by symmetry, we could do the other one, right? Now by symmetry, we know that G has a local max at X equals positive 3.14 because G prime changes from positive to negative, not in France where the fluvid's happening, but at X equals 3. This has to be negative as well. Thank you. You got to change both of them here. So I'm not going to write the other one, but there it is. And if we had to say something about every critical value, Ethan, what would we say about 0? Sleep talk if you need to. Talk in your sleep. G has neither a local max nor a local min at X equals 0. I didn't hear the what?
Because
G prime. Don't say the function. If you say the function, we're going to like, what function? Like a toaster, its function is to make bread toasty. We play stupid. Because what? What are we talking about? Because G prime is positive on, what's the magic word? Either side of X equals 0. There you go. Okay. There you go. There you go. So I made this question because I wanted to force us to use the calculator, but really we could have done this one by hand. If you said X cubed equal to 0, you get 0. If you hit sine of X equal to 0, where is sine equal to 0 on the unit circle? Yeah, on the unit circle, sine is 0 and y is 0, which is at 0. So that's like a double critical value. Pi, 2 pi. But if we go backwards the rotation, negative pi, negative 2 pi. So negative 2 pi is outside. That's negative 6. So, but I wanted to use the calculator. So anyway, the point I'm trying to make is when you have a graph of G prime, it's better than a number line. Because not only do you get the signs of the derivative, you get their relative values as well. Okay, so we just have to train ourselves to look at it in the correct way. All right. So far, so good. How are we doing on time now? A few minutes. See, it's hard to rush through this because there's so much fun.
so much to it.
Don't waste fun.
No.
Yeah. All right. Example 6. I'll tell you how old these questions are. T is for Tate on A, J is for Jenna on B. K is for Corpy. We only have time for one of them. Who do I pick? My son's flying into DC tomorrow for his internship, and they canceled 500 and something flights yesterday at DC airport. So there's a snowstorm coming in. Maybe your dad can just take him in his.
I guess.
Hop in the back. Your dad can fly him. Okay. Oh, your dad doesn't have one in the garage?
No. he
Okay.
does.
All right.
He wants one.
Let's just go ahead and jump into part A.
He's gonna get one soon.
Find the x coordinate of the relative extrema. Okay. Step 1. Sorry, I didn't mean to get off course. Step 1. What's the domain? What's the domain? What values of k give us outputs? We're trying to avoid division by 0. We have a denominator with a variable in it.
The domain is the K can't.
Tell me. Talk to me. It's all real numbers. Yeah. We can't take square roots of a negative, but we have a cube root. Negatives are fine, although it's not. And we don't have any denominator, or if this were to the -1th power, that would be a denominator in disguise, but it's not. So the domain is all real numbers. Now that's good, because if the derivative doesn't have a domain of all real numbers, those will be critical values. Now, we have to take the derivative. We can either distribute or use the product rule. I'm going to use the product rule because we need to review it. So to use the product rule, we need to rewrite this function. Oops, too fat. We need to rewrite this function as k to the 2/3 times 2k minus 1. And again, it's your prerogative whether you want to distribute that or not. At this point, though, you should be like ding, 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 ding. Cuss flirt once again, because we have a fractional exponent, 2/3, that's between 0 and 1. So what's the root of that base, or what's the root of the base? What value of k when you plug it in for k gives you 0? 0. So I know there's going to be a vertical tangent at 0. Okay, it might be a local max, it might be a local min, but maybe it's neither. But I already know that. We find the derivative. Maybe we can find some horizontal tangent lines as well, huh? So let's use the product rule. T prime, or what would y'all tell me? What would y'all do if y'all were left to your own devices? Would you distribute or product rule it? Probably distribute. I'm thinking because y'all like the power rule better. So let's go ahead and do it that way. Nothing wrong with that, right? We have the ability to, so we might as well use it. So 2k to the 1 plus 2/3, that's 1, right? So that's 5/3 minus k to the 2/3. Now remember, when we're using functions, we really like them factored. And it was given to us factored. So we like that. But to take the derivative, let's put it in a different form that's easier. All right, and now I'm shifting gears here. I'm going from t of k to t prime of k. So I can't just carry down the equal sign. And now it's just power rule, right? 5/3 times 2 is 10/3 times k to the 5/3 minus 1 is 2/3, right? And then minus 2/3 times k to the -1/3 third. Okay. And there's the derivative. Holy crap, we have to use that, don't we? We have to use that. We're going to have to like set it equal to 0 and see where it's undefined. Then we're going to have to plug it back in to figure out what the sign is. F that thing, right? F that thing. What did you say?
No.
Oh. When I say F that thing, I mean what? Factor that thing. Yeah, don't like, well, I don't know what's in your head. Farm it? What do you want to grow potatoes on there? Farm it? Factor it. Let's factor. Now, what is common in both terms? Let's look at the numbers first.
You could take out a negative.
And I would probably, well, look at the base, 10/3 and 2/3. They have what in common? 2/3. Okay, we'll factor out a 2/3. Now, this is what's interesting. They each have parts of k's, but what parts of k's do they have in common? This is your introduction to, we need to factor out least powers. If you factor out the smallest power, that's the one that they have in common. Like if you have x squared and x cubed, 2 is smaller than 3. So you can pull out the 2, x squared, right? Which number is smaller, 2/3 or -1/3? -1/3. So I can factor out an x to the -1/3. And now inside, I'm going to be left with 5k something and 2. I know it's going to be 2, right? Because I take the whole k to the -1/3 out. But it's going to be 5 times k to the what? Is it to the first?
If you take -1/3 out of 2/3.
Absolutely, because what does the rule say? When you're dividing, what do you do with the exponents? You subtract.
Elementary.
Oh, it's 1. Sorry. It's 1. I'm stressing because I heard people in the hallway walking, and I think the bell is getting close, and Hank started shuffling for his bag, and I just want to finish before the bell. Yes, it's supposed to be a K. Hey,
It's okay.
do as I say. Do as I say, not as I do. Haste makes waste. Stay focused. All right, yeah. let's finish this. When you factor out, you divide out. When you factor out, you divide out. We're factoring this negative 1/3 power out. So we're dividing out this negative 1/3 power. So imagine there's a horizontal line right here. K to the this divided by K to that. You would subtract the exponents, right? 2/3 minus a negative makes it plus 1/3. What's 2/3 plus a third? 3/3 or 1. So it's to the first power. Now, mentally redistribute. You know this pretty well. When you distribute, you're multiplying, you add the exponents, right? What is 1 plus negative a third? 2/3, okay? So you have to know which one that you're subtracting, which goes first, because it's not commutative. It's the top one minus the bottom one, exponents. Very good.
Oh, yeah.
Yeah,
Sounds better.
honky tonkin' Hank. Very good. So if we fix this now, let's come over here. T prime of K, last thing, it's going to be 2 times 5K minus 1 all over 3 times the cube root of K. And I think we have to stop right there. But we got it in the, or in this case, the prime form. That's harder to do. Nice. I'm hoping we can finish tomorrow. Thank you for allowing me to teach right through B lunch. Have a fantastic C lunch. You're welcome to stay as you've been doing. I'm going to hang out. I'm going to chill. Good times, good stuff. Oh, I'll get it. Some people failed geometry.